Good afternoon, ladies and gentlemen. I'm Shawn Isidro. My partners are Methujan Jeyapalan and Jaumdally. As you can see, we've selected the disc brake as our project. Very quickly, two issues or two design objectives of our design we want to achieve is maximum cooling and maximum braking. However, the problem is thermal induced stresses. So we're going to go over quickly our loading conditions, and then we're going to talk about how our final design meets our objectives.
So I'll be talking about the estimated fatigue life of the rotor. The material we used for the rotor was cast iron, which has ultimate tensile stress of 200 megapascals. First, we have to calculate the endurance limit, which can be found by multiplying the ideal endurance limit to the correction factors. The ideal endurance limit is half of the ultimate tensile strength, since the ultimate tensile strength is less than 1400 megapascals. So next, to find the surface factor, we assume the surface finish to be hot rolled, which then gives us our A and B values, which then we plug into the surface factor equation to get a value of 1.2854. And then for the size factor and loading factor, we assumed it to be 1. The temperature factor, we assumed the temperature to be 500 degrees, which then gave us our KD value. For the reliability factor, we assumed 99%. Which then gave us our KE value, and then multiplying everything together gives us an endurance limit of 80.36 MPa. So next we could find the fatigue life. So from the textbook we found out the fatigue strength fraction of 0.9 for an ultimate tensile stress of 200 MPa. We then plug in the values to find A and B, which then we plug into another equation. And assuming the completely reversible stress of 85 megapascals, we plug in that in the equation, we get the number of cycles as around 621,000 cycles.
Our next loading condition is the factor of safety. This is the term that essentially describes the load carrying capacity of a system beyond the expected loads. In other words, the factor of safety is how much stronger the system is than it needs to be for an intended load. This value indicates whether or not the design, which in this case is the rotor component of a FSAE disc brake, will be able to withstand the stress being applied to it. It is based on the fatigue failure, which originates due to stress concentration effects at the surface. As such, the most highly stressed points are on the outer surface for both axial and bending, where the crack originates on the outer surface and progresses inwardly. By using the appropriate dimensions, we calculated the bending stress and the axial stress, as well as the moment in the x direction and the moment of inertia. Here's the bending stress. And assuming a stress concentration factor of 2.5 for both axial and bending, we were able to calculate the maximum stress, as well as the alternating and the mean stress based on von Mises stress. By using the modified Goodman criterion, we were able to calculate the factor of safety. This is a good representation because this theory entails the alternating stress, the mean, the endurance stress, and the ultimate tensile stress of the material being used. Moreover, with this project, we achieved a safe and durable and viable design for the rotor component in a disc brake, taking in consideration the forces exerted for all the components in the brake system. With this, we demonstrated a factor of safety of 8.6 for static loading, which tells us that our design is relatively safe and will continue to function and not fracture.
So we conclude that our design is safe because the factor of safety is greater than 1 and that the expected lifetime is more than 600,000 cycles before replacement. So we will use two designs for our FSAE car to save cost. So one is the directional and pillar vane rotors, both of which have slots as shown. So here we have our directional vane rotor, and then we have our pillar vane, aka KBA kangaroo paw, or DBA kangaroo paw, sorry. And then we'll also have slots, as you can see here on the rotor face. So essentially, the slots reduce gas and dust buildup between the brake pad and rotor to maintain a consistent braking surface. And the vented rotors will help dissipate heat efficiently as provided in the animation on the left. Although many designs have cross-drilled holes, we do not believe that this is a suitable approach since they are prone to thermal cracking. To reduce heat buildup on the rotor face, we've inserted cooling fins on our brake pads that will take away heat from the entire caliper assembly. From our SolidWorks data, we see that the rotor face is relatively hot, but not more than 50 degrees during braking from top speed of 100 kilometers per hour to full stop. This is well below the 300 degree Celsius safety limit before failure. Hence, we believe our designs meet our objectives of maximum braking and cooling.